Better get this show on the road. My name is Matt Wright. I am the director of the Center for Cybersecurity at RIT. And I'm going to talk about how attackers could read your encrypted traffic and what maybe we could do about it. Now, what I just said might give you a little pause. Wait a second, you said encrypted traffic and the attacker's reading it. That's not supposed to happen. But consider the case of Shelly. Shelly, you see, Shelly has an embarrassing problem. Shelly has athlete shell. And as many of us do when we have a medical issue, we go online to check out her symptoms and see what she should do about it. So, of course, she goes to turtlehealth.com, as we all would, right? And, of course, she's using an encrypted connection because she wants to protect her privacy. And it's a good thing, too, because her snoopy neighbor Sheldon is trying to sniff on her wireless connection and read the traffic, but hey, it's encrypted, so all good, right? Unfortunately, turtles have more dangerous attackers to deal with. And what is it that Shredder is going to do? So Shredder is going to create his own connections to turtlehealth.com. And he's going to be doing this to perform an attack called website fingerprinting. The attack takes 2 steps. So first is this preparatory step, where he makes these connections himself, and he goes to, say, the shell page, the athlete shell page, and one to, like, curled tail disease or whatever it is. And when he goes to the athlete shell page, right, he sends HTTP GET request, gets some responses, sends some more requests, gets some more responses. But when he goes to the curled tail disease page, he gets a different pattern of requests and responses, different numbers of packets going back and forth. These create 2 patterns, P1 and P2, and he can save some information about these patterns into a database. So that's step 1. Step 2 of the attack is that he can actually perform the attack on Shelly. So Shelly is connecting to turtlehealth.com. Shredder is, again, sniffing the wireless traffic, and he's got his database, P1 and P2, and he sees that this is a match. This traffic going back and forth that Shelly is sending to the website is a match for P1. And so he says, oh, okay, well that means that Shelly probably has athlete shell. And it turns out that this attack is pretty effective. It's got, in sort of the prior literature, some 90+% accuracy. To convince you that this is an important attack, let's consider the different possible threats to Shelly's privacy here. So one is that, okay, it could be someone sniffing her wireless traffic, like I said. It could be someone who's compromised Shelly's DSL or cable modem router. And of course, we know how vulnerable these are with their default passwords and not being updated very frequently. It could be her ISP, right, or her workplace. And of course, the US Congress a couple years ago said, hey, ISPs, it is okay to spy on your customers. Oh, and go ahead and sell that data to other companies if you like. It could be any of the networks between her and the website, including, again, the ISP on this side over on the website side. So all of these are potential threats to use the website fingerprinting attack. So I would recommend to have a defense. The defense that I would suggest would be Tor. How many of you know what Tor is? Great. So we won't go through the whole thing, but the client is making these connections through a guard middle and exit node to get to the web server. That doesn't mean we completely prevent the attack. So the attacker in this case could be anybody sitting between the client and the guard. So almost all of the same attackers except for the ones that are close to the web server over there. Those are the ones who can see the identity of the client, right, the IP address of the client, but otherwise should not be able to see what website it is that Shelly's going to or what it is that she's looking at online. The way the website fingerprinting attack works on Tor is there's still the same 2-step process. Shredder's going to sit there and sniff his own connections through Tor to these different websites and generate a series of traffic patterns. He's going to then use those, feed them into a machine learning algorithm that's going to be used to train up a classifier. So that's the step one of the attack that he's preparing to do. Now notice one difference in the attack. Before we were looking at a specific website and pages in the site. Tor definitely makes the attack harder. One of the things it does is it breaks all the packets up into 512 byte chunks. So all the packets are basically the same size. That's definitely going to make the attack harder. And what the attacker is interested here is not which page within the website are you going to, but which website are you going to, right? Which is definitely going to be an easier attack, except that we're trying to do it over Tor. Step two of the attack, again, here's your user going over Tor to these websites. Shredder is going to sniff on that connection and see this traffic pattern, use the classifier to determine what website it is that Shelley is going to. In this case, WebMD. So it turns out that this attack has been around for a while, and it's been getting better and better as people have used different machine learning classifiers and different techniques to isolate the information. And in consequence, recently a couple of folks have proposed different defenses that could be used in Tor to improve Tor's defense against these attacks. One of these is walkie-talkie. The idea of walkie-talkie is pretty clever. You've got two websites, Site A and Site B. You're going to take their traffic patterns, you're going to merge them to create a single traffic pattern, and whenever the user goes to either Site A or Site B, you get that same traffic pattern. So in theory, you shouldn't be able to distinguish between the two sites, right? So the maximum possible accuracy should be about 50%. This adds some overhead to Tor, which is already it has some high overhead, and it adds 34% additional delay to Tor, which Tor is already pretty slow. If you've ever used it, you would already know that. So it does add some additional delay to Tor in order to provide this defense. But it works. At least it has worked in the past. Another defense is called WTF-pad. And this is something we actually worked on with the Tor project. The idea is fairly simple. You can have real bursts of packets. So if you look at web traffic, you got a really bursty behavior, a bunch of traffic and then less traffic and then more traffic. And if you look at the burst and then you look at another burst, there can be a gap in the middle. WTF-pad detects those gaps and fills them in with a dummy burst, like a fake burst of packets. This adds a little bit more overhead, but it doesn't specifically add delay. And it is considered the main candidate to be deployed in Tor. So it is something that is important to consider and study. So this is where we come in with the point of today's talk, is to talk about deep fingerprinting. This is work with my student PIUP, my former student Mohsen, and our colleague Mark from KU Leuven in Belgium. So you've all probably heard about deep learning. It's the new hotness and buzzwords, blah, blah, blah. And let me just give you kind of a quick refresh on why deep learning is such a hot new thing these days. So there's this data set called ImageNet. And there are 1.2 million images, 1,200 categories, so 1,000 images per category. And they're things like, okay, there's a horse, a table, a car, a ship, a banana, right? Can you, classifier, machine learning classifier, can you detect the difference between these things? Can you guess which one it is? In addition, there are 120 breeds of dog. This is one breed of dog, that's another breed of dog, that's another breed of dog. If you can tell the difference, you're probably better than me. The machine learning classifier is probably better than all of us these days. The reason that machine learning or deep learning has gotten so hot, so in 2011, that's the green bar on the far left, the error rate for giving the machine learning classifier 5 guesses. You've got 5 guesses. If you get the right class out of the 1,200 classes, if you get the right class, then you get it right, and otherwise you get it wrong. In 2011, the machine learning classifiers were getting it wrong 26% of the time. The next year, the first effective deep learning classifier came in and dropped that rate by almost 10%. It kept on dropping. We get to 2014. In 2014, it got to 6.7%, and one of the researchers in the field said, that's really impressive, but I think that humans can still do better. And he trained himself. And he sat there spending hours and hours looking at image after image to see if he could get really good. And he got it down to 5%. All right, humans are still better than computers. You know where that story goes. Next year, 3.6%, and it keeps getting better, right? So we have these algorithms that are really good at this specific task. They're superhuman, in fact, at these very precise, well-defined tasks. So can we give the website fingerprinting attacker a task, a well-defined task, that will also do the same type of thing? And to do that, we need to have a good data representation. The data representation we have is very simple. Remember that I said Tor, all the packets are the same size, essentially. So what we can do is just look at we have these outgoing bursts of packets from the client to the server, and we have these incoming bursts from the web server back to the client. And we say, okay, if it's outgoing, we say +1. And if it's incoming, we say -1. And that's it. That's the entire data representation. And that, it turns out, is all we need. Now, there has been some prior work in using deep learning to do website fingerprinting. Some of them were using the early, so CNN is a type of deep learning classifier. Some of the folks were using the one on the left, a design based on the AlexNet from 2012. But a lot of stuff has happened since then, and the accuracy of these things has gone up. And so by 2016, you have this Inception v4 network that was getting say 80% accuracy on the ImageNet set, where you only get one guess at a time. So given that, maybe we can take advantage of some of those advances and put them into our classifiers for website fingerprinting as well. In addition, we are interested to know, well, can we, there are these new defenses that I talked about. Can we break them, right? So essentially, you can think of it if you have an image, and now with the defenses, you've distorted the image. Can you still figure out, oh, that's a dog in the upper left-hand corner? And that's unknown. So the deep fingerprinting model, I'm not going to go into any of the details because I don't really have time, but basically we're just using some of the latest state-of-the-art machine learning techniques that are used in image classification and bringing them over to this traffic analysis world. One of the things that we use is we use deeper networks with more layers, and each layer, more stuff is happening. And what a good idea of what's going on is in images, you see on the far left, you have the low-level features that are in the shallow layers of the network. And that's looking for like the edges between light and dark, or one color and another. And as you get deeper into the network, you get more and more things. So by the third panel there, you're starting to see stripes or swirls or colors or curves, right? And by the far right, you can actually see in the bottom right-hand corner, those are wheels, right? You actually have visual features that you can recognize as a person. And that those are the things, the same features that the image classifier is using to pick out which class these things belong to. The same thing can be done for network traffic. On the far left, our low-level features are just the individual packets back and forth being sent. But as we get deeper into the network, we can look at the whole pattern of traffic, the ups and downs, and say, this is something recognizable for this website versus another website. So how does it do? Well, I wouldn't be talking to you now if it wasn't really successful, right? So we do get 98.3% performance against just vanilla Tor, like existing Tor as it is today. And of course, that in itself is dangerous. Now you can see that the prior state-of-the-art was getting some 97%, and I'm just going to argue, well, on the one hand, yeah, that doesn't look like a big leap. On the other hand, in the real world, when you're dealing with many potential more sites than we have in these lab conditions, that extra accuracy can actually make a difference. But perhaps more importantly, we also studied these things against defenses. And we have these two defenses. One is WTF-pad. And this, in our lab experiments, we're getting 64% bandwidth overhead, so really high bandwidth overheads, even with all of that extra dummy traffic, these fake bursts that are being added. We're able to get 90.7% accuracy. So the defense, the one that is most intended to be used in Tor, does not look very safe right now. What about walkie-talkie? Well, walkie-talkie does better. Remember, it merges these two sites. So the best theoretical maximum accuracy is 50%. We get 49.7%. I think what's maybe worse is that we can, if you give the classifier 2 guesses, it basically nails it. It's got a 98.4% accuracy in that case. So the walkie-talkie defense, I also wouldn't really recommend. All right, so in conclusion, we've looked at Tor and we've looked at applying these deep learning models to do the website fingerprinting attack on Tor. And it turns out it works pretty well. The deep learning models, a deeper deep learning model is more effective using all the state-of-the-art techniques. And it also can be effective against distorted traffic, essentially, like these distorted images over here, still being able to recognize which image or which website is which class. And with that, Shredder is back, and a quick shout out to the National Science Foundation who funded all this, and with that, I'll take any questions. Yes, sir. Right, so we actually have a couple of techniques. Oh, yeah. So the question is, do you have any other defenses since these two are broken? We are working on a couple of things. It turns out there are ways to trick deep learning mechanisms. So there's this really cool stuff like you can take a stop sign and you can put some weird stickers on it, and you can make it so that the deep learning classifier looks at that. Let's say it's in a self-driving car, and it looks at that and goes, oh, that's a 45-mile-an-hour sign. So that should probably also give you pause. But yeah, so there are potential defenses against these things. Any other questions?
Would a home computer have the power needed to run this kind of network, or is this network only feasible on a botnet side?
So the interesting thing about this, so if you have a GPU, although usually, you know, your laptop GPU, just sort of right now, the way things are set up, it's a little hard to get the deep learning models to actually use the GPU, but you don't need a very fancy machine. So if you've got, let's say $2,500 to put together a machine, you can get a reasonable machine with a $1,000 or $1,500 GPU in it. It'll work. Yeah, the deep learning models are getting really, like it's, the GPUs are really well designed to deal with this, and NVIDIA is just, their main product these days is not, well, I mean, I'm sure there's a lot of gaming, but there's a lot of deep learning. That's a huge product for them. All right, well, thank you very much.